Hello everyone, this is Dr. Young here, and in this video we're going to start to talk about enolates and how we can manipulate them and what the difference is between a kinetic enolate and a thermodynamic enolate. Right, so first let's talk about enols. Just remind ourselves what enols are, right? Those were the things, that's when you had an alcohol on an alkene. Right, and we said that when we had an enol, that those tended to tautomerize back to the keto form, right? So I could call this the keto form, and this would be your enol, right? And so, and this just kind of happens, right? This tautomerization was the name of that process. Anytime you have a carbonyl compound, there's going to be some small percentage of the enol. What can help, though, is adding an acid. So if, for example, you want an enol, and we'll see that in later videos, if you have an acid, this helps with enol formation. It just makes the equilibrium slightly more favorable because you protonate that O. But we don't have to worry about that right now. We'll talk more about that when we talk about acid-catalyzed aldol reactions and acid-catalyzed alpha halogenations. But for right now, I just want to remind you what enols are, right? It's the when you have an alcohol on an alkene. Now, an enolate occurs when you deprotonate a carbonyl compound, right? So if I add some sort of base, and I'll leave it generic for now, but I have some kind of base here. The idea is that remember we said that we have those relatively acidic hydrogens. I'm going to pick the set on the right. It doesn't matter if it's the right-hand side or the left-hand side. But if I have my base take off these hydrogens, right, I'm going to get what's called the enolate. So now I've got an anion here. And remember that we said that these were so stable because they are delocalized through the carbonyls, right? So this molecule, I need to draw two Lewis structures to best represent it, right? It's got resonance contributors. And this would be considered the enolate, right? Because if you look at it, it looks kind of like an enol, right? This thing over here. Let me erase that weird line. The idea is that this kind of looks like a enol. Right, so looks like an enol, but it's the anion. And hence the 8, right? So you change the ending to 8 because that's a delocalized anion ending. So it's an enol 8. It's an enolate. So we'd call this whole thing on the right-hand side, right? This would be the enolate ion. Right? It looks like an enol, but it's an anion. So the enolate. And that's we're talking a lot about enolates for this chapter, for this stuff. We're going to have enolate intermediates for most of the reactions, especially all of those base-catalyzed ones. So then what happens if we actually have an asymmetric carbonyl compound where I have different sets of alpha hydrogens that are not the same? Right, in that previous example with that 3-pentanone, I think it was, it didn't matter which set of alpha hydrogens you plucked off, it'd be the same thing because it was symmetric, right? This is not symmetric. I have an alpha spot over here on the left and I have an alpha spot over here on the right-hand side. And I'll draw these in green here, but on the left-hand side I have 1 alpha hydrogen, and on the right-hand side I have 3 alpha hydrogens. So it's going to make a difference, right, if I pluck one off from the left-hand side or the right-hand side, right? I can imagine a base, some generic base, taking off one of those alpha hydrogens on the right-hand side, or sorry, the left-hand side, for example. That would give me an enolate where I have that anion on that sort of isopropyl-looking group. And I'll draw the resonance contributor. Right, so that would give me 1 enolate. Or I could remove it from the right-hand side. Again, I'll leave the base generic here. We'll talk about big bases, small bases, strong and weak ones in a little bit. Or I could have a base take off one of these other ones on the right-hand side. If I do that, I get the anion over there on that methyl group. So, right, clearly two very different enolates. On the right-hand side, we have the anion on the methyl group and the alkene going off to the right. On the left-hand side, we have the anion on that sort of isopropyl group on a tertiary carbon, and then alkene going off to the left. So, and let me write here too, if I want to analyze, I want to know which one of these is the better one. So let me also make a note here that if I look at these resonance contributors, right, we said before that having the negative on the O is much more stable. So probably the bottom ones are our major contributors. So major when you have the anion on the oxygen, minor when it's on the carbon. So the real molecule mostly looks like the bottom ones. And I want to know which one is more stable, right? I want to know which one is going to be the lower energy enolate, which one's going to be the more stable one. And they're kind of similar, right, in that they both have a negative carbon, they both have a negative O, so nothing immediately jumps out there. But if you look at these two things, right, we said that the major is this molecule, right? The major is this, where it looks like an alkene. Right, you have kind of like a CC double bond and then a negative O on it. And it turns out that the stability of enolates follows that of the stability of alkenes, right? If you remember way back when, we said that the stability of alkenes depends on how many substituents there are on it. So that's what I'm going to use to kind of figure out how stable these alkenes are also. Is how substituted are these? The more substituted enolate is the more stable enolate. So for this alkene right here, right, if I look at this, I just see that it only has one carbon group coming off of it, right? It just has this one carbon group coming off of it. If I look at the alkene on the left-hand side, the enolate on the left-hand side, I see 1, 2, 3 groups coming off of it. So that's going to be more stable, right? This alkene has 3 substituents. This one only has 1 substituent. And by substituents, right, I mean carbon groups coming off. So that means this was the more, I'll put more stable alkene, and therefore it's the more stable enolate. This one has, this one is less stable alkene, and therefore it's the less stable enolate. So if you have your druthers, right, if you're going to use a tiny base, it can get to either one of those suckers, then you're going to form primarily the one on the left because it is more substituted as the more stable one. You probably just heard in the way that I spoke, though, this should start ringing a bell from back when we did E2 reactions, right? If you have a small base and you did an E2 reaction, you form the more stable alkene, which was the more substituted alkene. It's the same idea here. If you have a small base, and we'll talk about this more in a second, if you have a smaller base, it's easy to get to that spot over there on the left, that tertiary spot, and so you can make the more stable enolate. But you might imagine that if you have a big base, you have to go over to the right-hand side because it's just less sterically hindered. And so it's easier to get to and therefore faster. And again, this is just like when we did E2 reactions. We said big bulky bases like T-butoxide or something like that, right, has the easier time getting to the less substituted carbon because of steric interactions. So let me kind of remind you about that in this next slide here. All right, so let's take a look at this molecule. Here we have an asymmetric ketone. Remember that in that first one, we actually had a symmetric ketone. It was, what was it, 3-pentanone, I believe it was. And so it didn't matter which alpha hydrogens we took off. They were equivalent. They were the same. But here we have different ones, right? So I'm going to redraw this molecule so we can kind of talk about this a little bit. So here's the molecule. And I'm just going to call the hydrogens on the right-hand side the green ones. The alpha ones on the right-hand side are the green ones. And the alpha hydrogen on the left-hand side will be the blue ones, right? So I've got the green set and the blue set. And so we're going to take our ketone, we're going to add some sort of base, and we're going to produce our 2 enolates. right? So I'll draw one of the enolates here. The more stable one, right, is going to be the lower energy one. So I'll have the alkene going off to the left, so it's more substituted. And then on the right-hand side, and then for the other one, we will have the alkene going to the right-hand side, and then I'll have the O- there. And this is as good a time as any to start talking about this kinetic versus thermodynamic enolates. Like we've talked about before in the past, kinetic versus thermodynamic products, that just refers to the thermodynamic product is the more stable product, the kinetic product is the one that forms faster. So if I look at this one, right, the lower energy one is this one, so this is the thermodynamic product here, right? So this is the thermodynamic product. And that's because it's more stable. Right, so things want to get there. That's thermodynamically speaking, that's the most stable thing. That's the lowest energy thing. That's kind of what the whole chemical system is going for. Now, the one above it, though, is going to be the kinetic product, right? So thermodynamic product is this. The kinetic product is this one. And we'll see why in a second. Now, if I try to take off the green alpha hydrogen, right? So I'm going to go ahead and draw this line with green. If I take off the green one, we said that's going to give me the kinetic product. So I'm just going to draw just a regular old energy diagram hill here. All right, so here's my transition state. My transition state for if I want a base to come in and pluck off one of those green hydrogens, right? One of these alpha hydrogens here. It's going to cost some sort of energy, right? Because you're making and breaking bonds. You're bringing two molecules together. There's going to be some repulsion there. And then we'll get the kinetic product. Now, if I take and I try to take off this blue alpha hydrogen here, as I come in to take off that hydrogen, you'll notice that on the blue side, it's more substituted, so it's more crowded. Let me make a note of that, right? This is more sterically crowded. And so it comes with a cost. As you're bringing your base into that side, since it's a tertiary carbon, there's more stuff there, and so your base is going to bump into more things, right? It's going to start bumping into all of the hydrogens on the methyls that are attached there. And so our transition state for the blue route is you go, that one's actually higher in energy than it was for the green route, because on the green side, it's just a methyl. You come in there, you just bump into the methyls where you're at. If you come in on the blue side, you bump into, you bump into the hydrogens where you're at. On the blue side, you bump into methyls, right? So now there's all these extra groups. There's more steric interactions here. But after you hit that highest energy place, then you're allowed to go actually lower in energy to get to the thermodynamic product. And so what we really want to look at here is this difference between the energy levels of these two. Right? The difference between there and there is what's going to give you your kinetic control. And sometimes this is called the delta G double dagger, right? Because it's the difference between the delta G daggers, right? The activation energies. It's the difference between those. And so what we can say here, right, is if you have a large base, so large bases like T-butoxide, LDA, there's also extra ones like, you can imagine something like this. This is a lithium hexamethyl disilazide, where it's just got basically it looks like T-butyl groups, two T-butyl groups attached to that nitrogen. Just very big, very bulky. So for large bases, the delta G double dagger is large, right? And it's large because it's so bulky that when it comes into attack, that blue line is much, much larger, right? So when it comes into attack, its delta G is really, really, really big because it's large and it's going to bump into more things, right? It's more sterically hindered. Versus small bases are going to have a smaller delta G double dagger. So small bases Small bases, so, things like NaNH2, sodium hydroxide, stuff like that, right? They're going to have a small delta G double dagger because the base is so small, it's not going to really interact too much more with the tertiary side versus the methyl side, right? The left-hand side versus the right-hand side. It's not going to be that big of a difference. Yeah, it's going to bump into more things on the left-hand side, but not so much more that the difference in their transition energies is that large, right? So it's going to be much, much more similar. So it's not going to be as big of a difference. And that is going to be important for us because if I want to get more thermodynamic product, I am going to use a small base so it's not a big deal. So that the kinetics is not that big of an issue. Ditto, if I want to get more of the kinetic product, I'm going to use a large base because now the difference in the activation energies is big. It is going to be much, much larger because it's going to be much harder for a large base to get over the top of that hill is the idea. So if I want to summarize this here, right? So we said that this was the kinetic product. This is the kinetic enolate. And the one on the right or the left-hand side was the thermodynamic enolate. Again, it was thermodynamic because it's more stable because that alkene is more substituted. And if I want to get the thermodynamic enolate, what I want to do is I want to use a small base. And I want to do kind of warmer temperatures. Because I want to not have to worry about that activation energy difference being an issue. I want to have plenty of energy so I can overcome that higher activation energy to get to the more stable thermodynamic enolate. Also, these processes are reversible, so it allows us to go back and forth until we end up at that thermodynamic enolate. So you want warm temperatures. So that would mean like things like just, you'll see like room temperature, 20 degrees, maybe 30 degrees, something like that. You'll see something warm-ish. And then for the kinetic enolate, right, the idea is that we wanted very large bases. We wanted large bases so that they're kind of forced to go to the less substituted of the two carbons there, right? A large base can only get to one side, right? And for kinetic enolates, because we're talking about kinetics, I want it to only go the route that is the fastest route, right? So the one with the lower activation energy. So we want really cold temperatures, right? Because again, I'll draw this sort of with a real quick energy diagram here. The idea, again, if this is energy, and here's your starting ketone, and you have two different enolates, O minus, and then the other one's up top. Right, and we said we could go directly to the kinetic one, or we could go to the thermodynamic one. The idea, right, is we want to set low temperatures, right? We want the temperature to be like here so that we only have energy to go this route, right? We don't have enough energy to get over that other hill. So we want to have low temperatures so we can really only get to the kinetic one is the idea. So you want low temperatures. You want to keep the energy low, right? So that's how we do it. We lower the temperature. Now, I'm going to stop here for this video. I just want to kind of show you guys these two, but I'm going to go and give you a couple of examples of how we apply this, because now we're going to start using this to then start tacking on things in these alpha spots. And whether we go kinetic or thermodynamic is going to depend on what conditions we have. So let's take a look at that. Now, I am going to do a whole video on alpha alkylations and acylations and stuff, but here are just some examples so you can start wrapping your mind around what it is we're talking about here. So I'm going to make some notes here, right? So this is a two-step process, right? So if I look at this first one, it looks like I have this base and this temperature, right? This to me looks pretty warm. This is like room temperature, a little warmer. And this to me looks like a small base. So these two things together are screaming at me to go with the thermodynamic enolate. Right? It's warm and I have a small base. And again, if I look at my two alpha hydrogens, I've got one here and one here. This one is just a methyl group. And this one here is a primary group. Or actually, let me. I'm talking about them as groups, but let's just talk about what they are as carbons here. So let me erase that. Sorry. Right. Another way to say this is that this is a primary carbon and this is a secondary carbon. And so I'm trying to form the more stable enolate, right? Which means I'm going to go for the more stable side. So the enolate that I'm going to form is this one. And again, you know, I'll do more of these reactions later. If this is like, wait, what on earth are you talking about? Don't worry about that. But then the idea here is that step 2, I add CH3CH2Br. And so what we have now is we have a nucleophile, right? This thing is a nucleophile. And so what we're going to have it do is it just does an SN2 type reaction. This is just going to attack and do the backside attack. Right? Kick out the bromine. And what I'm going to end up doing is I put a carbon group on the alpha spot. Right? So here's my parent thing, and then I added 2 carbons, right? I just added these 2. I just added this piece to that alpha carbon on the right-hand side. Right, alpha, alpha. So I added that ethyl piece on the right-hand side. Now if I look at the second one here, now I've got a large base, and I've got cold temperatures. So now this is screaming at me kinetic. So go for the kinetic enolate. And if I look at the kinetic enolate, that's going to be on the other side. But it's going to be the same thing where in step 2, I add, it looks like this propyl iodide. And it's going to do the same thing. It's going to do an SN2 attack where the negative is going to attack the propyl iodide to give me a product here. Where again, if I redraw my parent carbonyl, the alpha spot on the left-hand side now was the thing that attacked that propyl group. So then I'm going to add 3 more carbons onto that alpha spot. So 1, 2, 3. So then I made that product, right? So the first one made this. The second one made this. So I was actually able to control which alpha carbon ended up attacking that electrophilic alkyl halide in the second step. And again, we're going to do a lot more examples of this in a following video, but just this is where we're going. This is why we care about the size of the base and the temperature and stuff like that. And then for this last one down here, I just want to make a note that not every molecule is going to have this issue about kinetic versus thermodynamic. Again, here, this one down here, the cyclopentanone here is symmetric, so there is no difference. If you go left versus right, it doesn't matter. So you can kind of use whatever conditions you want, right? So here's a big base and warm temperatures. So that's kind of not great for either kinetic or thermodynamic, but it doesn't matter here because you don't need to worry about kinetic or thermodynamic. Either set you take off is going to give you the same product, right? So you're either going to get let's see, you're going to get this and this. And in this case, we're adding the benzyl bromide. But it does the same thing. It does that SN2 to give you your product. Which would look like that. So this would be another example of an alkylation. So don't stress out too much if this seemed like a whole bunch of gibberish, but hopefully you got enough out of these last few examples that you're like, oh, I can control where I want the negative charge. And so in the next video, we'll talk about alkylations, alpha alkylations, and acylations in more detail. So study up. Good luck. If you have any questions, please let me know. Take care.